In the previous video, we constructed a user interface for our pipeline program and learned about several of Python's text mode tools along the way. In this video, we will learn how to execute and control other programs from within our own, allowing us to create the heart of our example program. This ability is often useful for all sorts of system automation tasks. Making other programs run used to be something of a mess. There were different mechanisms that worked on different platforms. There were mechanisms that were convenient, and there were different mechanisms that were secure. Fortunately, that all changed in Python version 2.4 with the introduction of the Subprocess module, which abstracts away the differences between platforms and makes the more secure paradigms easy to use. There are 6 objects in the Subprocess package that are of particular interest. 3 of them are the call, check call, and check output functions, which are 3 variants on the same basic idea. They run a program, wait for it to terminate, and then tell us something about what the program did. The call function returns the program's exit code, which is an integer that has a program defined. Defined meaning, which is usually used to know whether the program has succeeded or failed. The check call function raises an exception if the program's exit code is non-zero, which by convention means that it exited with an error. The check output function returns whatever text the program printed and raises an exception if the program exited with a non-zero exit code. The raised exception has an attribute called output that contains the text output of the program, so even if the program exited with an error code, we could still get the output if we want it. The run function, which is new in version 3.5 of Python, is similar to the call function we were looking at just a moment ago. In fact, it is capable of doing anything that anyone would do in combination. However, being new to 3.5, it is not necessarily possible to use it in other projects, at least not yet. The 3 call functions and the run function are invoked in largely the same way. Each of them is passed a list containing the program name and its arguments. We see the output of this function ls-l on the screen. That wasn't from the call because ls-l prints something out when it runs. The exit code returns 0 though. That becomes your call. If you wanted to take that printout from the ls program and use it in our program, we need to capture. The check output function has a noteworthy keyword-only parameter called universal_newlines, which defaults to false. If we set to universal newlines to true, the text output of the program is decoded into Unicode characters using the system's default text code C codec, and new line characters are normalized. If we leave universal_newlines at its default value of false, the program output is returned as bytes, and it's up to us to do any decoding and to deal with whatever sequence of characters the current system considers to be a new line character. In this case here, we did set it to true and then split it on the \n, which is the standard new line character, and that gave us back a list of the lines that are output from the program. If we want to get fancier with our running of other programs, we'll want to use instances of the popen class, the 4th interesting thing in the Subprocess package, and which allows us a great deal of flexibility and control over the execution of other programs. At the cost of a bit more complexity, the popen constructor accepts the same list of program and command line arguments that the call functions do, and a very large number of optional keyword arguments, including universal_new lines. We're going to focus on a particular use of popen that is useful, but goes beyond what we can achieve using one of the call functions. We're going to see how to run a program in the background, while our own code is also running, and send and receive data between the two programs. To manage that, we're going to need the last of our 6 interesting things in the subprocess package, the pipe constant. The pipe constant is used in conjunction with the standard in, standard out, or standard error, standard error. Keyword parameters of popen constructor. Those parameters represent the other program's textual input, output, and error reporting. And any of them that we set to pipe are redirected to our program. In this example, we're redirecting the program's input and output to ourselves, which gives us a bidirectional data channel with the other program. So now you see we are interacting programmatically with the code on screen. That was at the beginning of this example. But since it sets in a loop, inputs and then outputs accord, and whatever it input. Once we have the pipe set up, we could send data to the other program by calling the write method on the popen object's standard in attribute. And we could read data by calling the read method or its relatives on the popen object's standard out attribute. In spite of disabling buffering with the buff size equals 0 parameter to the popen constructor, it's usually a good idea to call the flush method on standard in after writing to it, and on standard out before reading from it. We could keep on sending and receiving data for as long as both programs are running, but if the time comes when we're done interacting and just want to wait for the other program to terminate, we could call the popen object's wait method to do that. The wait method will return the exit code of the other program once it's done running. A lot of the complexity of working with piped standard in and standard out is wrapped up in the popen class's communicate method, which accepts the input as a parameter and returns the output. Communicate is simple, but somewhat limited. Communication is simple, but somewhat limited because it can only be called once for each popen object and doesn't return until the other program finishes. That isn't any good for 2 programs that need to talk back and forth to each other. But it should be just perfect for our pipeline program, where each program receives the output of the previous program as its input. We're going to create a bunch of classes to represent the different kinds of steps in the pipeline, and integrate those classes into the interface as well. Once we've done that, the program is functional, although there's plenty of room for improvement. Our particular interest is the exec step class on the top right of the screen right now, which uses popen to actually execute a program and break free of the output. We've got our example program working now, so we're going to move on to the last topic in the section, setting up a shell script or batch file to launch the program.